What if everything you think you know about the most familiar substance on Earth is wrong? What if the very thing that keeps you alive is quietly breaking the rules of physics at every moment? Water is not just ordinary matter. It is a contradiction, a collection of at least 7 major physical anomalies that should not exist together in a single molecule, and yet they do. Without them, this planet would be lifeless, frozen, and silent. No oceans, no forests. No blood flowing through veins. In fact, no you. Because if water behaved like a normal molecule of similar size and mass, Earth would never have become a cradle for life in the first place. To understand why, we have to begin with a single, almost invisible force inside the water molecule itself. Everything starts with oxygen. Oxygen is not gentle in the way it interacts with electrons. It is aggressive, almost greedy. On the electronegativity scale, which measures how strongly an atom pulls shared electrons toward itself, oxygen ranks extremely high. Only fluorine is stronger. So when oxygen bonds with hydrogen to form water, it doesn't share electrons equally. It pulls them closer to itself, bending the balance of the entire molecule. This uneven pull creates something unusual. The oxygen side becomes slightly negative, while the hydrogen side becomes slightly positive. It is not a full charge like in ions, but a subtle separation of electrical force. This makes the water molecule a permanent electric dipole, a tiny but powerful imbalance built directly into its structure. That might sound like a minor detail, but it changes everything that comes next. Because of this dipole, each water molecule can interact with others in a very special way. A single water molecule has 2 hydrogen atoms and 2 pairs of electrons that are not involved in bonding. This allows it to connect with up to 4 neighboring water molecules at the same time. 2 connections come from its hydrogen atoms, and 2 more from its electron pairs. The result is not a random liquid, but a constantly forming and breaking network. These connections are called hydrogen bonds, and they are far stronger than the weak forces that usually hold small molecules together. In fact, they are about 10 times stronger than typical intermolecular attractions found in similar substances. This is why water behaves so differently from molecules that look almost identical on paper. Take methane, for example. Its molecular weight is almost the same as water's. By simple logic, you would expect similar behavior. But methane becomes a gas at temperatures where water remains liquid. Methane boils at around minus 161 degrees Celsius. Water does not boil until 100 degrees Celsius. That is a difference of 261 degrees caused entirely by hydrogen bonding. If you didn't know about this hidden structure, you would predict water to behave like methane. You would expect it to vanish into gas at room temperature. And that would be a reasonable scientific guess based only on mass. But water refuses to follow that expectation. Instead, it builds a constantly shifting network where bonds form and break in trillions of a second. At any given moment, there is a structured lattice of attraction holding molecules together. Even though each individual bond is temporary, it is stable without being static, organized without being fixed. And this is only the beginning of its strange behavior. As we move deeper into this invisible network, something even more surprising appears. Water is not just held together by hydrogen bonds, it is defined by them. Every property we observe in liquid water depends on this constantly rebuilding structure. At any moment, hydrogen bonds are forming, breaking, and reforming at extraordinary speed. Each bond lasts only a few picoseconds, a timescale so short it is almost impossible to imagine. Yet despite this constant collapse and reconstruction, the overall network remains intact. It behaves like a living structure, always shifting but never falling apart. Now, to truly appreciate how unusual this is, we need to compare it with other substances. Most liquids are held together by weak, fleeting forces. These are called van der Waals interactions, and they are fragile. They barely hold molecules together, which is why many substances with similar mass to water easily become gases at room temperature. Water refuses to behave this way. Its hydrogen bonding network is far stronger, creating a level of cohesion that is completely unexpected for such a light molecule. This becomes even clearer when we compare boiling points. A substance like methane, with nearly identical molecular weight to water, boils at extremely low temperatures. It requires deep freezing conditions to remain liquid. But water remains stable as a liquid across a wide range of temperatures where life thrives. This difference is not small, it is massive and fundamental. Without hydrogen bonding, water would behave like a volatile gas, drifting away into the atmosphere and eventually into space over geological time. Earth would never have retained oceans long enough for life to evolve. Instead, water forms a temporary but continuous network, a dynamic scaffold that gives it strength far beyond what its molecular weight suggests. At any given instant, each molecule is connected to others in multiple directions, forming a constantly shifting but coherent structure. This structure is the foundation for everything else water does. It is the reason it can resist temperature changes, the reason it expands in strange ways when frozen, and the reason it can support life at all. But the next anomaly is even more shocking, because it breaks one of the most universal rules in physics. In almost every known substance, cooling leads to contraction. As temperature drops, molecules slow down, pack more tightly, and the solid becomes denser than the liquid. This is true for metals, gases, organic compounds, and virtually every material ever studied, except water. When water freezes, something extraordinary happens inside that hydrogen bond network. Instead of collapsing into a tighter structure, the molecules lock into a rigid geometric arrangement. They form a hexagonal lattice, a repeating pattern with open spaces built directly into its structure. These empty spaces are not accidental. They are the result of hydrogen bonds locking water molecules into fixed angles and distances. As a result, the solid form of water actually takes up more space than the liquid form. This is why ice floats. This simple fact, something most people learn in school without a second thought, is actually one of the most important physical properties in the entire universe as we know it. Ice floats, and that single behavior prevents Earth from becoming an uninhabitable frozen world. To understand why, imagine a world where ice behaves normally, where it sinks instead of floating. At first, everything seems fine. A lake begins to freeze in winter, just like it does today. The surface layer cools and forms ice. But instead of staying on top, that ice sinks to the bottom. Now, the exposed water above it is still liquid, but it is open to the cold air, so it freezes too, and that new ice also sinks. Layer after layer, ice accumulates at the bottom of the lake. Over time, the entire lake freezes solid from the bottom upward, and once this process begins, it does not stop easily. Each winter adds more ice, building permanent frozen layers that never fully thaw. The lake becomes a solid block of ice trapped beneath liquid water that is quickly disappearing. Now extend this process across the entire planet. Rivers, lakes, shallow seas, coastal regions, all begin to freeze in this destructive cycle. With each ice age, more ice accumulates and less water remains liquid. Because ice is white, it reflects sunlight back into space, reducing heat absorption and accelerating global cooling. This creates a feedback loop. More ice leads to more reflection. More reflection leads to less heat. Less heat leads to more ice. The planet spirals into deeper and deeper freezing conditions. Eventually, Earth could enter a full snowball state, where almost the entire surface is locked in ice. And unlike seasonal ice ages, this would not easily reverse. The planet could remain frozen for millions of years. Geological evidence suggests that Earth once came dangerously close to this state roughly 700 million years ago. Entire oceans may have been nearly sealed in ice, with only small regions of open water remaining near the equator. And yet, Earth survived. Life persisted. The reason is simple and almost unbelievable. Ice floats. Because ice stays on the surface, it forms a protective layer instead of sinking. This layer insulates the water beneath, preventing the entire ocean from freezing solid. It allows ecosystems to survive through extreme winters and recover when conditions improve. If ice had sunk, Earth's history would have been completely different. Complex life might never have emerged. There would be no forests, no animals, no human civilization. And all of this depends on something incredibly specific: the angle between hydrogen atoms in a water molecule, precisely 104.5 degrees. That angle is not arbitrary. It is determined by the quantum behavior of electrons around the oxygen atom. It defines the geometry of the entire water molecule, and through it, the structure of ice itself. Because of this fixed angle, water molecules arrange themselves into a hexagonal lattice when they freeze. That open structure is what makes ice less dense than liquid water. A single geometric constraint at the atomic level decides whether a planet freezes to death or remains habitable. And the consequences go far beyond oceans and ice caps. Right now, your body is mostly water. Roughly 60% of you is this same molecule, behaving according to the same strange rules. Your blood, your cells, your brain chemistry, everything depends on water functioning exactly as it does. But water does something else that is equally important for life. It is one of the most powerful temperature stabilizers on Earth. This is due to an unusually high specific heat capacity. Water can absorb enormous amounts of energy without changing temperature quickly. When heat enters water, much of that energy is not immediately converted into motion. Instead, it is absorbed by the hydrogen bond network, stretching and rearranging those connections. This means water resists rapid temperature change. It takes a massive amount of energy to significantly alter its temperature. On a planetary scale, this creates stability. Oceans act like thermal buffers for Earth. They absorb heat during the day and release it slowly at night. They smooth out extreme temperature differences between seasons and regions, This is why coastal cities have milder climates than inland areas. The ocean regulates the atmosphere above it, distributing energy over time instead of allowing sudden temperature spikes. Without this property, Earth would experience extreme fluctuations. Days would be scorching, nights freezing, weather systems would be unstable and violent. Instead, the oceans create balance. This same principle can be felt in simple everyday life. Water holds heat far longer than metal. A warm bath stays warm. A metal pan cools quickly. The difference is not coincidence. It is the hydrogen bond network again, absorbing and releasing energy at a controlled pace. On Mars, where liquid water is not stable on the surface, temperatures swing wildly by hundreds of degrees between day and night. There is no ocean to buffer those changes. On Earth, water smooths everything out. This stabilizing effect is not limited to temperature alone. It extends into the very chemistry of life itself. Water is an extraordinary solvent. Its dipole structure allows it to interact with a wide range of substances, breaking apart ionic compounds and surrounding individual ions with molecular precision. When salt enters water, something remarkable happens at the microscopic level. The oxygen side of water molecules, which carries a slight negative charge, is drawn to positively charged sodium ions. Meanwhile, the hydrogen side, slightly positive, is attracted to chloride ions. Water molecules surround each ion from all directions, gradually pulling them away from the crystal structure. The ionic bonds holding the salt together are overwhelmed by these interactions. The crystal disintegrates, not through force or heat, but through pure electromagnetic attraction. This ability makes water the most versatile solvent in nature. It can dissolve more substances than most liquids, allowing complex chemistry to take place inside it. And this is essential for biology. Inside your body, water carries oxygen, nutrients, salts, hormones, and waste products all at once. Blood is not just fluid. It is a carefully balanced chemical solution made possible by water's unique properties. Even more importantly, life's most complex processes depend on this environment. Protein folding, enzyme reactions, DNA replication, and cellular respiration all occur in aqueous solution. Without water's ability to dissolve and transport molecules, none of these processes could function. This is why life as we know it is tied so closely to water. Not because it is abundant, but because it is chemically unmatched. But even this is not the final layer of its strange behavior. Water also has one of the highest surface tensions of any non-metallic liquid. At its surface, molecules are pulled inward by their neighbors, creating a kind of invisible skin. This allows water to form droplets, resist external force, and even support small objects on its surface. It is also the reason insects can walk on water without sinking. More importantly, this surface tension enables capillary action, where water can climb upward against gravity in narrow spaces. Adhesion pulls water toward surfaces, while cohesion drags neighboring molecules along. This is not just a laboratory curiosity. It is what allows trees to exist. In tall trees, water must travel from roots to leaves over distances exceeding 100 meters. There are no pumps, no mechanical systems. Instead, water is pulled upward through microscopic tubes by evaporation at the top. As water evaporates from leaves, it pulls the next molecule upward, which pulls the next, creating a continuous chain of hydrogen-bonded molecules stretching from root to canopy. Gravity is constantly pulling downward, yet the hydrogen bond network holds the entire column together under tension. In some of the tallest trees on Earth, this system operates at its absolute limit. The water inside these columns is under negative pressure, meaning it is being pulled apart rather than pushed together. It exists in a delicate balance where a single disruption can break the entire chain. At extreme heights, this tension becomes so intense that the water column begins to fail. Tiny gas bubbles form inside the liquid, expanding rapidly and breaking the continuity of flow. This process is called cavitation, and once it happens, the transport pathway is permanently disrupted. This is not a biological limitation. It is a physical one. Trees could, in theory, grow taller, but the properties of water itself prevent it. Even the tallest living organisms on Earth are constrained not by genetics, but by the strength of hydrogen bonds resisting gravity. And yet, water's influence goes even deeper. Its dipole nature allows it to break apart solid crystals like salt. When salt enters water, each ion is pulled apart by surrounding molecules, dissolving the crystal structure completely. This is not a chemical reaction in the traditional sense. It is a mechanical separation driven by electromagnetic attraction. Because of this, water can dissolve more substances than almost any other liquid. This is why oceans contain traces of nearly every element on the periodic table. It is why blood can carry such a complex mixture of dissolved compounds. It is why cellular chemistry is possible at all. Every biological system depends on this dissolving power. Without it, nutrients could not circulate, signals could not travel, and metabolic reactions would collapse. So when we step back and look at everything together, a pattern emerges. Water floats ice, stabilizes climate, resists temperature change, dissolves complex substances, enables biological chemistry, and even defines the maximum height of trees. Each property reinforces the others, forming a tightly connected system of physical anomalies. And all of it originates from one simple molecular detail, an angle of 104.5 degrees. A single geometric constraint in a tiny molecule determines whether a planet is dead or alive. So the next time you see water, remember that you are not looking at an ordinary liquid. You are looking at a substance that continuously bends the rules of physics just enough to make life possible. If you want more deep explorations like this, subscribe and stay with the channel, because what we are just beginning to understand about the universe is far stranger than it looks on the surface.